1.5 infinite limits. So when I say infinite limits, I mean our answer is most likely going to be infinity, either plus or minus, and maybe because of both, our answer is going to be does not exist, like the limit doesn't exist. To start off with infinite limits, we need to revise vertical asymptotes. If you recall, here's a graph of the reciprocal function, f of x equals 1 over x. And for the reciprocal function, there is a vertical asymptote. So right at 0, um, the graph doesn't actually pass over 0. Um, from the left, let me get a different color here, green. From the left, my graph ends up going down to negative infinity, right? Right here. And then on the right, so here, my graph ends up going up to positive infinity. So if I were looking for the limit of this function, so like let's say the limit as x approaches 0 of this function, I would have to actually say, oh, it doesn't exist. Now, the limit from the right, okay, so like let's say I'm now changing this, and I add a little plus right there, so from the right, then my answer would have to be infinity. But what if I change it again and just, make that go away? Oops. And instead of from the right, from the left, then my answer would actually be, oops, oopsie, from the left, it would be negative infinity. So that's what today's lesson is, and we're using vertical asymptotes to determine these limits, which are usually headed towards in some kind of infinity. Sometimes both, therefore not existent. This is the formal definition for an asymptote. The line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit from the right, because it's a plusy plus, the limit from the right is plus or minus infinity. Sorry, I'm trying to erase this and it won't cooperate. Okay. Or the limit from the left is plus or minus infinity. So for example 1, we're finding vertical asymptotes algebraically. And hopefully you remember how to do this. If not, it's actually really easy. All you have to do is take the denominator and solve for its 0. So you're going to find, well, let me write this down. Okay, so find the 0 of the denominator. Now, there's an exception, and that is a whole. Before you look for vertical asymptotes, you want to make sure that there aren't any holes in the equation, so you would factor those out first. Okay. For these two, I don't have, but for the next example, there is a hole. So we're just going to go ahead and do A right now. So I'm going to take the denominator, and I'm just going to set it equal to 0. Right? I'm going to find a 0. So let's see, equals 0. You can distribute 2x plus 2 equals 0. So subtract 2 from both sides, divide by 2, and I get negative 1. Or you could be wise and then like, ooh, this is already factored. I mean, that 2 is just a number. It doesn't have an x with it. So let me just take this, x plus 1, and of course it's just going to be negative 1. Okay? So there's really not much you can do to mess this up, as long as you take the denominator and set it equal to 0, after you factored out any holes. I didn't have anything to factor for A. Now for B, you could probably take a good close look at this. The bottom, the denominator, I know it's a difference of squares, so I could very easily factor that, but the top, it's no. We're not going to factor that. There's no easy factoring there. So I can't or will not find a hole. So you just set the denominator equal to 0 and solve. Or, because it is a difference of squares and so easy to find its factors, its potential, or its binomials, then you can just do that. So again, I'll do both ways. Why not? You could take x squared minus 1, set it equal to 0, add 1 to both sides. Got to get rid of the square, and the only way to do that is to square root. So x equals potentially plus or minus 1, right? Because the square of 1, so 1 squared gives you 1, but negative 1 squared also gives you 1. The other way would be to use the factored version, and then, oh look, x minus 1 equals 0, so that means x equals 1. And then x plus 1 equals 0, which means x equals negative 1. Whichever, one or the other. But now, these are my locations of my vertical asymptotes. So I'm going to go back to part A. Let me split this up. And then you could say, ooh, there's a vertical asymptote at x equals negative 1. And then for part B, you'd say there's a vertical asymptote at x equals negative 1 and just, oops, not negative 1 again, 1. Okay? You can write the word and if you like. But that's basically that. Okay, example 2, determine all vertical asymptotes of the graph. So basically the same as example 1, only that here, right, because we're going to be careful, we want to make sure that there aren't any holes, and I already told you that there was. There's one nice little hole there. So factor out. The bottom is conveniently a difference of squares, right? So x minus 2 and x plus 2. Now the top, I need two numbers that multiply up to negative 8. Well, I know 2 and 4, right? But they have to add up to positive 2. So if the 2 is negative, I can get positive 2 after adding them, and negative 2 times 4 is negative 8. So then x minus 2 and then x plus 4. And there's the hole, right? The graph doesn't exist at x equals 2. So there's a hole at x equals 2. Okay? And then, so really now all I have left is just x plus 4 and x plus 2. And so now to find the vertical asymptote, I still take the denominator, set it equal to 0, right? Find it 0. And so therefore, now I have a vertical asymptote at x equals negative 2. And that's that. See, here, if you did not take out the hole, you would be telling me, ooh, there's a vertical asymptote at negative 2 and positive 2. And then that would be wrong. So it's really important that you eliminate the holes to begin with. Factor them out. All right, example 3. Determine the limit of each function as x approaches 1 from the left and from the right. So we're finding the limits of both of these graphs, but the two-sided limits, the left and the right, or the one-sided limits, sorry. Okay, so I'm just going to write that out real quick. Make the graphs a little smaller. Okay, so I wrote it out, right? We're going to do the left-sided limit and the right-sided limit. So for A, as my graph approaches 1, and let me pick out a color. Okay, so as my graph approaches 1 from the left side, see here? Oh, my computer's freaking out. Where is my graph headed? It's headed towards positive infinity. So my left-hand sided limit would be positive infinity. And so now I'll do the same, but for my right-sided limit. So from the right, it's headed up again, also to positive infinity. So my right-hand limit is also positive infinity. And then if you look, my vertical asymptote was at 1. And we did have a function right here. And as you can see, the denominator, if I were to actually figure out what the vertical asymptote was, the vertical asymptote was at 1. Okay? Vertical asymptotes are an indication that the limit there is infinity, some form of infinity. That's basically today's lesson here. All right, so now we're going to repeat. Same thing with B. So from the left, my graph, oh, look at that, also going to positive infinity. But then from the right, as x approaches, or my graph is getting closer to 1, right, it is headed towards negative infinity. So A, we had the same answer, no big deal. B, we had two different answers. Now see, sometimes you'll need like a specific sided limit. For A, since both of them are infinity, you could say the limit overall is infinity, but infinity is still subject to be called, you know, non-existent. B, they're different infinities. One is plus, one is minus. So we would still call this also non-existent. Okay, the non-existent thing is kind of tricky because infinity doesn't actually exist because there is no limit to the number infinity is, right? Um, so either it doesn't exist because the what are these called? The limits didn't match, or it doesn't exist because, well, even though these did match right here, right? And I'm looking over here, even though they did match, it's still infinity, and who knows what that is. Okay, example 4 says determining infinite limits numerically. So we're going to do this the long way, using numbers. So I've already done all that for you. I'm going to fill in the numbers, right? Okay, so these are the numbers I chose because I want numbers that are really close to the number 1 because our limit that we're looking for here, right here, is as x approaching 1. Okay, so 0.9, 0.99, 0.999, right? Because the further along here we go, the closer these numbers get to 1. Now on the right side, I'm trying to get these numbers also close to 1. So 1.001, and then 1.01, and then 1.1. So then the idea is that you would plug in every single one of these numbers into this equation to get out your f of x. Of course, I've done that already. Okay, so here are my values, and examining my limits here, or rather what my numbers are doing, or my behavior, my function behavior. The closer I get to 1 from the left side, what's happening to these numbers? I started off with basically 19, and then basically like 200, and then 2,000. Okay, they're getting bigger and bigger, right? Substantially. So it is safe to say that from the left, we're headed towards positive infinity. So now you're going to basically emulate that idea onto the right side and figure out what's happening there. So basically I started with negative 21, and then negative 201, and now negative 2001. So it's getting more and more negative. These numbers are getting smaller and smaller and smaller in the idea that negative numbers, the bigger the actual number is, since it's negative, it's actually really small. But either way, we're getting more and more negative. So negative infinity. And so here's a case where I'd be like, okay, so the limit actually doesn't exist, right? Because one side is going up like this, and then the other side is going down like that. So we would say it does not exist. Now, if I were to ask you for x plus 1 from the left side, then you best say positive infinity. If I were to ask you for the limit as x approaches 1 from the right side, then you should say negative infinity. All right, so determine each limit. What? Determine if each limit. Oh no, wow, I can't read. Determine each limit's existence. Boy. Okay, so we're trying to figure out if the limit exists. And again, you know, this is not a simple direct substitution. I can't actually plug in the 3 here because I'm going to end up with 0 as a denominator. Same for b. So first things first. Vertical asymptotes. See if there are any vertical asymptotes. But, you know, keep in mind the existence of holes because you got to get rid of those first. But I actually can't factor A or B, so there aren't any holes here, people. So x squared minus 9, right, which is basically x plus or minus 3. So then right now you should easily be able to tell me, ooh, there's a vertical asymptote at negative 3 and there's a vertical asymptote at positive 3, right? So vertical, oh, let me write that down. Vertical asymptote at x equals negative 3 and positive 3. Now our limit, let me highlight that. Our limit right here is as x approaches 3. So then we're basically focusing on this dude. I know there's a vertical asymptote, which means most likely this graph is doing something like this or like this at 3. So we're going to know, right off the bat, ooh, it's not going to exist. B, same idea. Think about it. Okay, there's a vertical asymptote at x equals 1. So you know that, there's something along these lines, right? Maybe something like that. Maybe it's going down instead of up, something. So that should click in your brain that, oh, okay, the limit's not going to exist. So we would say DNE. Okay, same idea. Now, if one-sided limits are different, and honestly, the only way you could tell the one-sided limit is to either do like example 4 and do it numerically or graph this function. Okay, so yeah. Okay. Example 6, determine each limit's existence. Now, limits have a property where I could actually just figure out the limit of this first part, right? Because you've done this already, hopefully. And the limit of this part, and then just add them. So that's what we're going to do. And we're going to use a little bit of function analysis here, peoples. Okay, so the limit as x approaches 0 for 1, I have nothing to plug in, so it's going to be 1. Now, for 1 over x squared, ooh, Mrs. Rondon, there's a vertical asymptote at x equals 0, right? Because the denominator, set it equal to 0, solve for x. So let's see. I get x equals plus or minus 0, no such thing, right? So x equals 0, there's a vertical asymptote. So vertical asymptote means some kind of infinity is happening, right? Okay, so I don't have a graph to go off of, and I'm going to pretend that it's impossible for me to actually graph this. Okay, so we're going to have to rely on other things, like our brains. So for the second part there, let me make this in red. For this part right here, right, we figured out that there's a vertical asymptote at x equals 0, but that could mean several things. That could mean that it's doing this at 0, right? That's one scenario. Or it's doing like one of these, It could be, the limit could be positive infinity, it could be both, or I haven't done negative infinity. Okay, so we got to figure out which one it could be, and it's simple to do by analyzing this function. It's 1 over x squared. Is there any way that I can make this 1 over x squared negative? Think about it. Oh my god, I'm trying to erase this dot. Okay. Is there any number I can plug in here that will make this number negative? Hopefully you're like, no, that's a square. Squares are never negative, right? So negative 3 squared is positive 9. So that's a good indicator that, oh yeah, nothing about this can be negative. So there's no way that it can be this. And no way it could be this. It has to be this scenario. So therefore, it's 1 plus infinity. This would be the limit for 1 over x squared. All right, so now you're like, wait, what's 1 plus infinity? Well, see, what's special about adding just one more to infinity is it's still infinity, ladies and gentlemen. So my answer would be, let me get rid of all this gibberish. Okay, the limit as x approaches 0 for this function here is just infinity. Basically repeat for b. But, looky, I had to make it complicated, right? It's a one-sided limit. Okay, so for 2, well, the limit as x approaches 0 from the positive side of 2 is, well, no matter what, still 2. Because I have nothing to plug the 0 into. There's no x there. Now for here, ooh, that's the reciprocal function. See, function analysis is going to work in that we need our memories. Okay, the reciprocal function look like this, right? So you know that from the left side, it's going to be negative infinity. But as it approaches 0 from the right side, it is positive infinity. So then you're like, oh, okay, so this is plus, also positive infinity. In which case, the answer is just infinity, because even though I'm adding 2, I'm not really changing infinity. Infinity is supposed to mean forever, all, right? But do take note, right? There is also a vertical asymptote here. I just didn't think I had to actually write it out. So you do know that there's something happening there. But the reciprocal function is a function, a parent function that you should like have in memory anyway. Um, Also from the positive side, all these numbers would be positive. So that's another indicator there. Okay, done. You should have your notes all written out. And you need to work on the problems. You need to do as much as you possibly can and then bring your questions to class, not the whole homework. You should be able to do some of this.